Hey guys! Welcome to my fifth and final Physics 2211 lab report. Today I'm going to give us a little throwback to the beginning of the semester with balanced forces. This time though, I will be investigating the force applied to an object on a ramp. First, I want to refresh y'all on some important concepts for today's lab. Newton's second law states that the force applied to an object is equal to that object's mass times the acceleration of that object. For the object I'm using in my lab, the acceleration will be the acceleration due to gravity, which is 9.81 meters per second squared. The forces that are present in this system will be the force of gravity and the force of friction. Because our forces are on a ramp, the forces will be constructed a little differently than usual. Traditionally, when constructing a force diagram, you account for all the forces on the axes, but in this case, the force of friction is at an angle theta. To account for this, I break the force of gravity into its components so there will be a force parallel and perpendicular to the force of friction. I like to think of it like rotating the axis by theta and then breaking up gravity to fit on those axes. Because of the location of angle theta in the bottom right corner of the ramp, the x component of the force of gravity would be represented by Fg sine theta, while the y component would be represented by Fg cosine theta. Now on to the actual application of these processes in my experiment. I took a video of myself releasing a cardboard box to run down a cardboard ramp that was placed at a 30-degree angle relative to the ground. I put the video into Tracker and tracked its motion before exporting and analyzing the data. Next, I created a model using Python to represent my data. Let me take a second to explain my code a little bit. I started out by creating a white background to show my model. I then created the visualized characteristics of the model, the ball, the trail, and a small point to represent the origin. Next, I set up my graphs to measure both position versus time and velocity versus time. I set my constants next, the mass of the ball, the acceleration due to gravity, the coefficient of friction, which I looked up on the internet, and the angle of the ramp. I then set the initial position and velocity of my model. Because my object was initially at rest, I made the initial velocity 0. The last thing I did before coding my loop was set the initial time to 0 and the time step. In the loop, I calculated the force of gravity and the force of friction for each iteration and used those values to calculate the net force. I then updated the position and velocity using Newton's second law and advanced the clock by delta t. I updated the ball's position on the track and plotted the data values on the graphs. Finally, I ran my code and collected the data from my model. When I run my model, you can see the ball moving toward the bottom right of the field, much like my initial video. Looking at the graphs, you can see that the position time graph increased non-linearly. This means the velocity, which is the slope of the position time graph, was not constant, and there was an acceleration of the object over the time interval. This is further proven when looking at the velocity time graph, which shows that the velocity increases linearly over time. This shows that the acceleration of the object, or the slope of the velocity time graph, was constant throughout. A very interesting relationship is seen when you compare the experimental data and the model data. As the sliding object picks up speed, the difference between the model data curve and the experimental data curve increases. Judging by the r-squared value of the experimental and model data, the model is a more ideal representation between the position-time relationship of an object sliding down a ramp. This may have occurred because my model negates air resistance, a force that would become more and more important as the velocity increases. One of the markers of increased air resistance is decreasing the rate of change of velocity and thus decreasing the rate of change of position, much like what occurred in my experimental data. So that about wraps up my final physics lab. Hope you enjoyed this series and stay tuned for more content in the future.